Hello students, this is the third lecture under the series Magnetic Effect of Electric Current. Today we will learn about force on a current carrying conductor in a magnetic field. This topic looks a bit complex. We will understand it after we do these experiments. So first of all we know that Hans Christian Ørsted, a most known scientist, he demonstrated that if a current carrying conductor, suppose this is a copper wire, a conductor, it is having a current is passed through this conductor like this. So we know that a magnetic field, it is developed around this conductor in the form of concentric rings. It means the electric current, it produces magnetic field in a conductor, and we know how we know that magnetic field is created by the magnetic field lines. This is one thing. Now suppose we have this magnet, horseshoe shaped magnet. This is the north pole and this is the south pole. We know that these strong magnets, they also have their own magnetic field, and this also we know by magnetic field lines, and we know that the magnetic field between these two poles of this horseshoe shaped magnet is from north to south. The field lines, they run from north to south, and this is the magnetic field of this magnet. This is the magnetic field of this conductor. It is produced only when the current is passed in this conductor. So both are having magnetic field. Suppose this conductor is put inside this magnet or put near this magnet. What will happen? The magnetic field of this conductor as well as the magnetic field of this magnet, they will interact with each other. When there will be an interaction, then a force will be produced, and this force will be experienced by this conductor, and this conductor will be dislocated, or it moves from its original position due to the interaction of magnetic fields in between these two. A force is developed. We will further explain this phenomena by a simple experiment. So here is the experiment. What is this? This is a horseshoe shaped magnet, and it is known as, we call it as external magnet. This will produce its magnetic field, which will be like from north to south. The magnetic lines will be from north to south, like this. This is a magnet. This red color is a aluminium rod around 5 centimeters in length, and it is placed in between the two poles of this magnet. Suppose the magnet is like this, and this rod is put like this, perpendicular to the field of magnetic field of magnet. This is the magnet, and this rod is put like this in between the two poles, which is horizontal in position and at right angle to the field of this magnet, like this. So this rod, now it is tied at two ends. Suppose this is A end and this end is B end. So at A and B, it is tied with a wire. This wire is a connecting wire, and this is a stand, this is a rod. Through this rod, this wire is, connecting wire is supported, and it is joined by a battery from where current can pass in this aluminium rod. So this is the apparatus. Now what we do next, we switch on this switch. This is the positive end and this is positive and this is negative. The current will pass from this positive end with along with these arrows. Here it goes like this, and it comes to B end of the aluminium rod. Then it passes through the aluminium rod. It is a conductor, comes to A, and from A through this wire it comes back to the battery. A complete circuit is formed. So in this way the current is passing from B to A. When current is passing from B to A, what happened? A magnetic field developed around this aluminium rod. We know the current carrying conductors, they form a magnetic field around them like this in the form of concentric rings. And this rod is in between this horseshoe shaped magnet, and this magnet is also having magnetic field which is running from north to south. These are two poles. What happens when current is passed, this is also exerting force on this magnet, and magnetic field of this magnet also exerting force on this rod. When the force is experienced by this rod, it displaces from its original position. It is like this. Before it is like this. When current is passed, it goes inside. It displaces to the left. So when current is passed, in the first place, it comes inside the horseshoe shaped magnet like this. It displaces to the left. Now the current is switched off. It again comes to its original position. Now again at second time, when the current is switched on, what happens? The battery terminals, they are interchanged. Then what will happen? Now the current, this will be the plus, this will be the minus. When they are interchanged, now the current will go like this, and now it will run in this aluminium rod from A to B, and from B it comes back to the battery. When the direction of the current is reversed, what happened? This rod, it comes outside. It displaces towards the right. Suppose this is the rod. When the current condition is reversed, it comes out. It deflects towards the right side. First, this is the stationary position. In first case, it displaces towards the left side. Now it displaces towards the right side. And this displacement is due to the force which is being experienced by this rod due to the magnetic field of external magnet. This is one thing. So what we conclude? We conclude that the force is dependent on direction of current. This is the first point. If the current is changed, the direction of the force is changed. To what we are calling force? The displacement of the rod is force. The rod is displaces due to force, and this force, it is dependent on the direction of current. The second thing we can demonstrate, if the amount of current is increased, more current, heavy current is passed in this aluminium rod, then the displacement is more. It goes further to this side or farther to this side. So the second point is force is directly proportional to the amount of current. So this is the second point we understand. Now one more. Here we are seeing that North Pole is on the lower side and South Pole is on the upper side. if we flip the sides of this magnet, suppose now we put the North Pole on the above side and South Pole on the lower side. If these two poles are flipped, then also the direction of the force is flipped. The direction is changed. Suppose in this position it is going in, then if the position is reversed, it will go out. So the third point is force is dependent on the direction of magnetic field of external magnet. This is external magnet. So the magnetic field, this is the external magnet. So the magnetic field of external magnet also determines the direction of force. So these 3 points we have demonstrated by this simple experiment. Now many experiments are done to show these points, and Ampere, one of the scientists on whose name the unit of current is there, Ampere, he also demonstrated that this experiment shows the relationship between force, direction of force, direction of current and direction of magnetic field. Later on, he demonstrated that this is motor principle, which we will study in the next video. So, how we know the current, the relationship in between these 3 things? What are these 3 things? They are, so we want to establish a relationship between force, direction of force, second current, direction of current, and third direction of magnetic field. We want a simple rule to demonstrate the relationship between these 3. And this rule is proposed by the most famous scientist, Fleming. And the rule is known as Fleming's left-hand rule. This rule suggested the direction of these 3 but not the magnitude of the force. If we know the current, if we know the magnetic field, like here current we know, magnetic field we know, so we can calculate or we can say from in which direction the force will be applied, the force will be experienced, and this we can demonstrate by this Fleming's left hand rule, though it does not give anything about the magnitude of the force, but the direction of the force can be demonstrated by Fleming's left hand rule. So what is Fleming's left hand rule? I have just draw this hand. Does it looks like a hand or no? So this is a hand. So what we have to do, how we know on which direction the force is going? So first, this is my left hand. First you form like this, a gun. This is the situation of the gun. First form with thumb and forefinger a structure like a gun. Then open the middle finger or the center finger. So this is the first forefinger, this is the center finger, and this is the thumb, and this is left hand. Again make a gun, then open this finger. So what we are seeing, this and this are at right angle. This is 90-degree angle. Thumb and this finger is at 90-degree. This and this finger is at 90-degree. So all 3 are at 90-degree to each other. That all these 3 are perpendicular to each other. So we have to make our hand like this. All these 3 should be perpendicular. This finger is forefinger. So this demonstrates field. or magnetic field. F for forefinger, F for field. So this finger, it tells us about the direction of magnetic field. This is the center finger, and C for center, C for current, and this finger tells us the direction of current. This is thumb, T for thumb and T for thrust also. And thrust and force, they are one and the same thing. So the direction of the thumb shows us the direction of force. And we start from these knuckles. Suppose I want to say the direction of current. So I will say from this side to this side, from knuckle to nail. From here, from knuckle to nail. So start from here and ends here. So this is how the left hand, this is how the Fleming's left hand rule. Suppose I want to know the force. I have told you that the first of all this rod, it goes in. The force is on the left hand side. So we will prove that it is according to Fleming's left hand rule. See how. This is my left hand. What is the direction of field? Magnetic field is in this way. So this finger shows the direction of field from bottom to top. So, and this is the direction of current from B to A. So it should be like this, from B to A. I have told you we have to start from knuckle. So this is B and this is A. And this is magnetic field from north to south. This is the direction of current. Now where is my this thumb? My thumb is towards the, so this how, right, left. So my thumb is, this is like this is like this, and my thumb is towards the inner side of this magnet. So it goes in. Suppose the direction is changed and now the direction is like this. This will be the same because north-south pole are same. Now the direction of this current, it is changed from A to B. Now the thumb is towards outer side. So this rod will go out towards the right hand side, and previously it was going towards the left hand side. So this can be proved by Fleming's left hand rule, and later we will learn the Fleming's left hand rule. It is used in motor principle. If we know current and magnetic field, then force can be known, which is the direction of force. Now this is a small question based on this rule. Suppose this is the direction of magnetic field, this side, and this is the direction of electron. Electron is coming perpendicularly to this magnetic field. We want to know what is the direction of force, in which direction this electron will be displaced. So how can we know? If force is asked and current and field is given, we have to apply Fleming's left hand rule, and it is also known as Fleming left hand rule. And there is one more, Fleming's right hand rule, which we will learn later. So Fleming's, or you can write Fleming left hand rule. So if current is given, MF is given, and force is asked, then we have to apply Fleming's left hand rule. So how will we solve this question? I will take my left hand, MF, this finger is for MF, field. So I put my finger like this. This is electron. Electron is for current. But we know, conventionally, we take the current from positive side. from proton. Actually the current is of flow of electron, but conventionally we take the current direction from positive side. So we will reverse the direction of this electron. So we will take the direction of the current like this, opposite to the direction of electron. So this is MF, and from north to south was the electron, but we have to take the current from south to north. So I will do like this. From south to north is the current. This is the field. What is the direction of the force? Direction of the force will be, or we can say, if I do like this, or if I do like this, this is field, this is the direction of current from south to north, and this is the direction of force. Direction, the force will go towards downside. So it will be downward. This is MF. This is the direction of current. The force will be downwards. So this is how we can solve certain numericals based on Fleming's left hand rule when current and magnetic field are given. This is all for today. We will learn next motor and motor principle. Thank you.